I know all of you think that math is wonderful and fun to do just by itself. If we're going to use the Kobelka-Munk equation, we really need some practical application for it. One of the main uses of the Kobelka-Munk equation is to calculate color amounts in most color matching software like we've described, but it can also be used to compare two colorants. We can compare concentrations, we can compare strengths, compare economic value, make dispersion time evaluations. So there's uses of the equation in its simple form that can give us information about colorants we are working with. We can use the simple version of the Kobelka-Munk equation in a practical example, and that's what we'll do. Let's say that you buy a particular blue pigment from a certain supplier, and he's been selling it to you for years, so you're used to him, and you pay a certain amount of money for it. Now your brother-in-law gets a new job with a competing pigment supplier, and he wants you to be his first customer. So he comes in and is trying to sell you a blue pigment to replace the blue pigment you're using. He comes in and says he can save you money if you buy his blue pigment because it's less expensive. Now unfortunately, you know his track record for honesty. You decide not to take his word for it, but you actually want to test his claim. This is one example of how we can use the Kobelka-Munk. We can analyze the value, monetary value, and see if it's a good value to change pigments. We use the equation, and the equation we use again is K over S equals 1 minus R, that quantity is squared, and we divide it by 2 times R. Again, R is the percent reflection from the photometric curve of the pigment as a tint, and usually we use tints because mass tones, which are just the colorant, are not good for strength evaluations. We pick wavelength of maximum absorption to calculate this K and S value. This is typically how it's done. Remember, this equation has to be done at a specific wavelength. Generally, the wavelength that's picked is the one of maximum absorption, and that's the lowest point on the curve. Then we can use a table to find K and S values for each sample. So we don't actually have to solve this equation, because if we know, like I said before, the K and S value, then we can look up R on the table. If we know R from the spectral curve, we can look up K and S on the table. All the spectral photometric curves that follow are for tints. If you remember from before, tints, or they're called white letdowns, are defined as a single colorant mixed with white in a given resin at a specific ratio in colorant loading. The ratio in colorant loading must be the same to accurately compare two colorants. So we make up a tint of both colorants in the exact same loading in the exact same ratio. Typical ratios are 90-10 or 95-5. Typically in our lab we use 90-10 for inorganic colorants and 95-5 for organic colorants. And that is the ratio of white. Almost always we use TiO2 to colorant ratio. So when we say 90-10, we mean 90% white and 10% colorant. So there's a lot more white than colorant that's used. From the next slide of the spectral curve of a blue pigment, we would pick the wavelength of maximum absorption, which is, for this pigment, 620 nanometers to make our calculations at. Now one note, the maximum wavelength of absorption is not always the best wavelength to choose in every case, but is typically the one is used. Sometimes you have to try a few different wavelengths to see if they work better in a particular colorant situation. For our cases, we'll use the wavelength of maximum absorption. So here's our spectral curve, and you can see at about 620 nanometers is where we have our lowest point. So that's where we'll do our calculations. Let's go back to our example. Your brother-in-law's supplier offers you a replacement for your standard blue pigment. The cost, you currently pay $10 a pound for your pigment. Your new supplier wants to charge you $9 a pound. He is saving you $1 a pound. Question is the new pigment the same chemical type of the pigment you are using? Because you can't change chemical types. or you'll end up having metamerism in your samples. And if it is the same type, is the new pigment worth buying? Is it worth it strength-wise compared to cost-wise? Again, here's our spectral curve for the current pigment, and we see that at 620 nanometers we have a 15% reflectance. Now if we can make a white letdown of our new pigment and also run a spectral curve on it, and what we have on our curve here is curve number 1 is our control or our standard, and curve number 2 is the new pigment. And at the same wavelength, curve number 2 has a reflectance of 17%, curve number 1 has a reflectance of 15%. We can see from the shapes of the two curves for the pigments that they have the same shape. This means they are of the same chemical type. So at least your brother-in-law is telling you the truth that you are the same chemical type. If you remember from earlier examples, that curve is a curve of phthalo blue, and you can tell by the dip or the shape of the curve on that right side where it absorbs. What about the strength? Are the strengths comparable? We can use a relationship between the strengths and the K and S values. The K and S values are proportional to the strengths of the two pigments. So we can set up a proportion, and hopefully you remember proportions from math class. You can say the K and S value of pigment number 1 divided by the K and S of pigment number 2 equals the strength of pigment number 1 divided by the strength of pigment number 2. Very simple relationship. We can use that to compare strengths. Now we will use this table on the next page to figure out our K and S values. K and S is one variable and percent reflections is the second variable. So like I said, with only two variables, if one is specified, the other is then known. From our spectral curves, we specify R, so we can look on our table to find K and S value. So for example, if we look on our table for R of 43.3, then we find it on our table, we see that at that reflectance, the K and S value is 0.371. Along with the course documents that I sent you, I sent a resource labeled K and S table. You can have a copy of the table to print out. Here's the table. Hopefully you can read the letters, but from our example, if you look at the reflectance percent 43.3 in the reflectance column, we move over to the K and S column and we see that it's 0.371. Again, you keep your control sample for this particular blue pigment. Its spectrophotometric curve is given again in the next slide. There's our control. The R value for the lowest point, 620 nanometers, is 15%. From our K and S table, we can see that the K and S value for 15% is 2.41. Then we can look at the curves again for both pigments. And one thing we can tell by just looking at the curves is that the curve for the new pigment is above the current pigment, so that tells us that it is weaker than our current pigment because it's lighter. The higher the curve, the lighter the value, or if we're talking about strength, the higher the curve, the weaker the pigment. The question is, how much weaker? So here's our two curves. Number 2 above number 1. There are two values for the reflectance values. The R value for 620 nanometers for curve number 2 is 17%. Look up on our table that the K and S value for 17% is 2.03. Then all we need to do is plug those values of K and S for 1 and 2 into our equation, and we can calculate the strength difference. Our KNS for pigment number 1 is 2.41. KNS for pigment number 2 is 2.03. And that equals the strength of 1 divided by the strength of 2. We can equate the strength of our control pigment to 1.0 and plug that in. So all we have is one unknown. So the strength of number 2 equals, we can cross multiply. So 2.41 times the strength of number 2 equals 2.03 times 1, or rearranging, the strength of pigment number 2 equals 2.03 divided by 2.41. Divide that out, and we see that the strength of number 2 is 84% as strong as pigment number 1. Now our cost, we take our cost differences, $9 divided by $10. Their pigment costs 90% of our original pigment, but only has 84% of the strength. So unfortunately, your brother-in-law is not coming to you with a good value. You're actually losing in this case. You're paying 90% of your original cost, but you're only getting 84% of your strength, original strength. So it would not be a good economical deal to change suppliers. It sadly appears your brother-in-law is trying to take advantage of you once again. But at least this time you can prove it, and you have data to back up your claim.